Okay. Cylindrical surface density. Cylindrical surface charges. There's 3 of them. They carry some surface charge, and we want to know the electric flux that passes through the closed surface of another radius, of another row, a larger row. So let's draw this problem out first. First of all, from the 3D perspective, it's going to look something like this. You have a cylinder, and they rise all the way up through C. But this is inefficient for the problem, okay? It's better to look at it from the XY point of view. So this, imagine we're looking down. Here's a little eyeball. We're looking down the Z-axis, okay? Here's our first circle. Second circle. And our second circle corresponds to these 2 values. Third circle. Okay. And the first cylinder in the graph, they're circles, but really they're cylinders. So we have 3 cylinders, and then we want to know how much flux goes through an even larger radius cylinder of 5 centimeters. Okay, well, it's actually pretty easy because we know by Gauss's law that the flux is going to be equal to the charge enclosed inside of it. And all that means is if you have some enclosed area, like this gray circle here, all of the charge inside the gray circle is going to come out. All the charge, all the flux of the charge, from the charge is going to leave perpendicular. So we know that the flux is going to be equal to the charge enclosed. So it's kind of going to look like that, leaving the surface. So all we have to do is find the charge of these 3 cylinders. Well, how do we find the charge? You're probably wondering. We can simply use our formula since we know, since rho s is known, we can use the equation Q is equal to the area multiplied by rho s dA. And we can even make that simpler, since we can see that these are uniform surface charge densities. We don't even need to integrate through it, because integration is used essentially to deal with non-uniform surface charges and things. Like if we need to integrate, like maybe the surface charge was growing through Z or growing, yeah, in this case it'd just be through Z. But maybe you had like a thicker cylinder, it's growing through rho or something. But in this case, we don't have to deal with that, so we can simplify it to A rho s. Okay. But then we also need to realize that we're going to have to do this 3 times, right? Because we're going to have to do this for this cylinder, and this cylinder. So Q total is going to equal Q1 plus Q2 plus Q3, right? We're just adding up the charges. Okay. So let's start with Q1. Well, the area, okay. Well, the area of a cylinder is 2 pi r L, right? And then rho s is given, and the rho s for the first one is 20. Centimeter. The length was given. The length is from 0 to 1 meter. So Z, which is also, we're calling ZL in this, is 1 meter. Right, 1.2 pico. Oh no, nano, 1.2 nano. Okay, Q2, same deal. 2 pi R is going to be 2 centimeters. Still 1 meter. -8 coulombs per meter squared. What does this one give me? Okay, and then Q3 is going to equal what's the and this is 0.94. So Q total again equals Q1, Q2, Q3. Q total equals, give me a second, 0.94 minus 1 plus 1.26. And that gives you 1.2 nanocoulombs. There you go. Thanks. Goodbye. Subscribe. Do whatever.